So in this problem, we were asked to look at the total energy of a simple harmonic oscillator. So in order to do that, we're going to first have to consider the kinetic energy and then the potential energy. So we can do this for any oscillator. That's sort of the beauty of simple harmonic oscillation. Let's start with just doing a simple mass on a spring. Okay, so the kinetic energy will be 1/2 mv squared. The potential energy will be 1/2 kx squared. If this is a new idea for you, this potential energy of a mass on a spring displaced by some distance x, you might recall that potential energy comes from the concept of work, and that work is a force integrated over some distance. The idea here is that the little bit that you might want to stretch out a spring is easy, but by the time you get it fully extended, that next little bit is much, much harder. Anyway, that's a bit of an aside. So we know that the solution for the simple harmonic oscillator is x is some amplitude sine omega t plus phi. Now, for our specific case, we know that omega is the square root of k over m. So let's continue on then. Let's start actually with the potential energy here. So we know what x is, so the potential energy is 1/2 kx squared. So I'll just write that out. A sine omega t plus phi squared. And the kinetic energy, which I sort of didn't really leave enough room for, did I? But the kinetic energy here is just 1/2 m. Well, what's v? V is just dx dt. So now we know that we need to actually take the derivative, and we have that k is 1/2 m. And now I'm going to take the derivative of sine, and I get a omega cosine omega t plus phi. Notice, by the way, as we take these derivatives, what's inside the sine and cosine? They never change. That's handy to remember. Okay, squared. So I compare these, and I notice that I have an a and a cosine and an a and a sine. And where I'm heading is that I remember that sine squared plus cosine squared is equal to 1. So the only thing I have to really worry about here are these things out front. So I have a 1/2 m, a 1/2 k, and this omega. But I realize that if I plug in, instead of omega squared, I use that omega squared is k over m, then the kinetic energy becomes 1/2 m, and k over m is omega squared. The m's cancel, and I'm left with a cosine squared. And now I realize these have exactly the same amplitude. So I can pull them out of the equation, and I find that the total energy is 1/2 times k a squared, now cosine squared plus sine squared. And this thing is just 1. So that means that the total energy is 1/2 k a squared. And that's a constant. So the total energy is the same, even though the potential and the kinetic energies are changing. So the kinetic energy, if it starts with maximum displacement, is a cosine squared. This potential energy is a sine squared. But the sum of those things is just a constant. Okay, we're done.